Here we go. Right, so very well. Good morning, everyone, and welcome to the Center for Theoretical and Computational Physics weekly seminar. Today, it is a pleasure to welcome Marjolein Dijkstra from the University of Utrecht in the Netherlands. Well, I've known Marjolein for quite some time. In fact, she did her PhD at Amolf Institute in Amsterdam, which I joined as a young postdoc many years ago. I don't think I'm going to say how many, but it was some years ago. Right, so after Marjolein was awarded her PhD from Utrecht University, she had a long postdoctoral career. And by the way, for those of you who are acquainted with the Dutch academic world, you know how much effort people put into designing beautiful covers for their PhD thesis. So I just thought I'd let you see the cover of Marjolein's thesis. Here it is. And I actually saw her do some of this work, which I'm honored to say that I did. So, as I said, Marjolein had a varied postdoctoral career. First, she was at Oxford. Then she joined Shell Research Labs for a short period, but then realized that industry was not for her and went back into academia, first in Bristol, then was it Lyon, Marjolein, that you were for a period? Okay, yeah. Then Bristol again, then you went back to the Netherlands, first as a researcher and then as a staff member. And she's steadily risen through the Dutch academic career, becoming a full professor at Utrecht in 2007, an appointment which she holds to this day. Okay, now, before I hand over to Mikko for a few words on his work together with Marjolein, just let me make two announcements of a more practical nature. First, this seminar is being recorded, so by staying on, you're giving consent to your voice and image being recorded and stored. And second, in the interests of internet stability, once the seminar starts in earnest, then I would ask everybody to mute their microphones and switch off their cameras, except the speaker, of course. If you wish to ask a question, you are, of course, free to unmute yourself and switch on your camera if you so desire. And now, enough from me. I'll hand over to Mikko for a few additional words of presentation. So, Mikko, the stage is yours now.
Thank you, Paolo. So good morning, everyone. So I would like to use this opportunity and to thank Marjolein for her support of our recently approved project on skyrmions, because she kindly agreed to be a consultant external, and this was very important to the final evaluation and success. So thank you, Marjolein, and I look forward to our future collaboration. So now, please, your stage.
To share my screen. I will start. Yeah, thank you very much for the introduction. It is a pleasure that this proposal was successful, and I'm looking forward to the collaboration. Today I would like to tell you about machine learning and inverse design of soft materials and what we have done so far concerning this in our group, the Soft Condensed Matter group at the Bij Institute for Nanomaterial Science at Utrecht University. And I first like to give you an extremely brief introduction to machine learning and soft matter, and then I will show you with several examples how we use machine learning to classify and find new order parameters that can be used to study nucleation in hard spheres and in binary mixtures of hard spheres, and how we can also use machine learning to find machine learning potentials where we integrate out one of the species in such a way that we arrive at effective interactions. And so we can coarse grain these soft matter systems. And finally, I will show you how one can also use machine learning to inverse design quasicrystals, liquid crystals, and crystals. So what is machine learning? Yeah, one can categorize it in two classes, supervised learning and unsupervised learning. In the case of supervised learning, one uses label data and one uses algorithms that are trained in such a way that the desired outcome will be gotten. And so you can train, for instance, an algorithm to distinguish pictures of cats or dogs, which are already labeled as cats and dogs. So you just give the algorithm pictures of cats that are labeled cat and pictures of dogs that are labeled dogs. And so you train this algorithm, and it's just a linear algebra procedure to adjust the weights and the biases, which are the training parameters, in such a way that the right outcome is received. And so the main application of supervised learning is either fitting if the output is continuous, or a discrete output in the case of classification. So in the case of unsupervised learning, you have unlabeled data. And so the algorithm that you then use tries to extract the most important features out of this data set, correlations. You can cluster your data, and you can use it as a dimensionality reduction method. And the dimensionality reduction method is very nice because that's all what we already do in statistical physics, where we don't care about the microscopic information, so all the particle coordinates and all the particle momenta, but you can describe a system also in terms of a few important thermodynamic variables. So it is, yeah, I think statistical physics was already way before machine learning or data science. So in our group, we are mostly interested in colloidal particles. One can make all kinds of particles nowadays due to many recent advances in the chemical synthesis. One can make colloidal particles that are perfectly spherical, that consist of clusters of spheres, dimple particles, rod-like particles, cubic particles, and so on. And these particles can be in the large colloidal domain, micron-sized particles, but one can also make nowadays nanoparticles. So one of the dimensions of these particles is below 100 nanometer. And these particles can be made of all kinds of materials. So one can make metallic particles, semiconductor particles, plastic particles, glassy particles, and so on. And so by using colloidal self-assembly, one can create nanostructured materials that can be used for functional advanced materials. And moreover, and that is even more important, is one can join the interactions between these particles in such a way that the van der Waals, the very strong van der Waals interactions due to all the atoms in these colloidal particles, are completely masked by, for instance, stabilization by charges or by steric stabilization. And so in most cases, one can join the interactions in such a way that the effective interactions are just hard interactions. And in that case, only the shape of these particles matter. So if we go to the simplest system, that of, for instance, hard spheres, so spherical particles that only interact with excluded volume interactions, then computer simulations in 1957 already showed that there's a spontaneous crystallization of such a system from a fluid phase to an ordered crystal phase. And the crystal phase is just a phase-centered cubic crystal phase. It's about a Becker fraction of a half, so when half of this volume is occupied by these spheres. And this was work by Alder and Wainwright and Wood and Jacobson, who showed this freezing transition. And so the question that one can ask is, and there's still dispute in the literature on how such a hard sphere crystal forms, one actually needs a good order parameter. If you really want to study nucleation, so the birth of this small embryo, the earliest crystal that is formed in a disordered fluid phase, one really needs an order parameter that can distinguish the particles, or basically the local neighborhood of that particle on a single particle level from all the other particles. And so the nucleation is really the birth of this nucleus, this small crystallite that starts to form. Due to thermal fluctuation, there are always many nuclei that appear and disappear all the time in the supersaturated fluid phase. But if this size of this embryo is larger than the critical size, it will keep on growing until it spans the whole system. And so already here we already draw the fluid particles 10 times smaller than the crystalline particles. So we already use some kind of order parameter. But if you really want to study nucleation, you really need an algorithm that can identify the local environment of every particle, can tell you whether it's in a fluid-like environment or whether it's in a solid-like environment. And so here, also if you want to distinguish whether it's a face-center cubic or a hexagonal closed-packed or a body-center cubic crystalline particle, you really have to look at the surrounding neighboring particles of a particular particle. So here I denoted the red spheres, and then I draw the neighboring particles around it. And one can clearly see that there's a difference between FCC particles, HCP particles, and BCC particles in their local environment. But these tiny changes are actually very subtle. So in the FCC particles, there's in all these cases, there's this hexagonal ring of 6 particles around the red particle, but then on top and at the bottom, there's a different arrangement of particles. So in the FCC phase, there's an hexagonal or a triangular arrangement of particles. The same in the hexagonal closed-packed particle, but the triangle is just pointing in the other direction. And in the BCC phase, there are basically 4 particles below and above this particle. So how can we distinguish these particles on a single particle level? And for that, we first have to define the local environment. That can be done very easily by just taking a certain distance, a cutoff distance, and then all the particles within that certain distance are called neighbors. One can also have more involved algorithms like the Voronoi construction or any other constructions. And then we just expand this local neighborhood in terms of spherical harmonics. And so one can then also average over all the neighbors for the QLMs. And then in the end, you also want to have a rotational invariant, because if you turn your crystal around, you don't want to your orbital parameter to fail. So you also make a rotational invariant by just summing over all the m values of the spherical harmonics. And then the Q6 and the Q4, because they measure the 4-fold and the 6-fold symmetry, are often used for crystallization, because most crystals have either a cubic symmetry or an hexagonal symmetry. But this is actually very dangerous, and I will show you why it is very dangerous. If you take, for instance, a fluid configuration, and for every particle in that fluid configuration, you calculate a Q6 value, so one of these bond order parameters, you will find this distribution for all the particles. You can do the same for typical face-center cubic configuration and the same for BCC configuration. And you clearly see that the Q6 value will increase if you go to the face-center cubic crystal phase. But the body-center cubic crystal is just lying in between the fluid and the FCC phase. And so if you study nucleation, then you will find that all your Q6 values of all your particles will go from a low value to a high value, and in between there is the BCC phase. And so you may conclude that nucleation proceeds via BCC. And there are several papers in the literature. Among one is from Dan Frankel, where they concluded that nucleation proceeds via BCC. If you try to be smarter and you plot all your distribution functions in the plane of a Q4 and a Q6 plane, you will see that there's a liquid phase, there's an HCP phase, it's intermediate Q4 and Q6, there's a tiny region where there's the BCC and there's the FCC phase. And then in panel B up to F, they just plot a simulation trajectory. And what they concluded here, and this was Kawasaki and Tanaka, they concluded that the fluid already shows some HCP ordering, and from these ordered regions, nucleation will start. And so if you look at a later time frames, you will see that it goes via the HCP region towards the FCC phase. And so here they really conclude that nucleation goes via HCP and not via BCC. And this all depends actually on the projection that you have taken. So if you just only project it on a Q6 axis, you will conclude it goes via BCC. If you plot it into a Q4, Q6 plane, you will conclude it goes via HCP. And this is actually the same with what we already know from football. It really depends on the projection if you conclude whether or not it is offside. So what we decided to do is, this is a full expansion spherical harmonics. You can also use the whole vector of Q values. So Q1 up to QD, and D a very large number. And so we did this, so we generate configurations using simulations. For every particle in that configuration, we calculate this Q vector that contains all the full expansion of these spherical harmonics, and then we just use a principal component analysis to find the relevant order parameters. So what is this principal component analysis? It is an unsupervised dimensionality reduction technique that basically uses a linear transformation of your reference frame in such a way that the principal component, the first axis, accounts for the largest possible variance, the second axis, the second principal component, the next largest possible variance of your data, etc., etc. So if you have data for this, all these blue dots as shown in this graph in the x1, x2 plane, a principal component will just give you the red axis and the green axis, which is orthogonal to the red axis, because the red axis clearly is the axis along which the data shows the largest variance. And so most of the information of your data is just contained by this linear transformation by the red axis. And so you can also calculate the eigenvalues for this new representation, and it gives you 0.98 and 0.02. So 98% of the information is really contained by this new red axis. And so that's what we have done. We used a fluid phase, and BCC phase, and FCC phase, and HCP phase. We plotted along the two principal components, and we immediately see that all the different clouds are now very well can be very well distinguished from each other. And more importantly, we can also see that the first principal component really tries to divide all the fluid from the crystalline phases. So the BCC, FCC, HCP are all at high principal component values, whereas the fluid is at low principal component values. And then the second principal component tries to divide the BCC from the FCC and HCP. And if you would have also plotted the third principal component that tries to separate the HCP from the FCC cloud. So we can now also use simulations, plot a simulation trajectory, your nucleation on top of it, and we find that it goes along the BCC cloud. It tries to avoid the BCC cloud, but also the HCP cloud. In the end, it also finds HCP because due to periodic boundary conditions, the FCC will just form stacking folds with the other image of the crystalline phase. We can also do that with experiments. These are experiments by Ernest van der Wey, Anna Nikolankova in the group of Alfons van Bladeren. They used a very nice trick. They could polymerize the solvent at different stages during the crystallization. And then because the particles are then completely stuck, you can just find all the particle positions of all your colloidal particles. And so also they were able to calculate all the bond order parameters and use this principal component analysis. And what they find is also it starts in the fluid phase, so it overlaps with the fluid cloud. And if you then continue at later stages, you will see that it also avoids basically the BCC cloud, and it goes very nicely to the FCC cloud. So it, in both cases, it just avoids BCC and HCP. So the next question that one can ask is, how does a binary crystal nucleate? And one of the most intriguing binary hard sphere crystals is the AB13 crystal phase. And this was already found in 2005 in experiments that if you have PMMA spheres, colloidal hard spheres, into different sizes with a size range of about a half, so the small sphere diameter is twice as small as the big sphere diameter, then there's a peculiar lattice that is formed that consists of a simple cubic of large spheres, and a simple cubic crystal is very uncommon for hard spheres, but with an extremely large lattice spacing in such a way that icosahedral clusters of 13 small spheres fits in the center of the simple cubic unit cell. And this is very peculiar because also all these icosahedral clusters of 13 small spheres, they are rotated by 90 degrees with respect to the neighboring clusters. So the unit cell of this AB13 crystal is extremely large. It consists of 88 of these icosahedral clusters of 13 small spheres, and then I can't count it that quickly, but in total there are 108 spheres in the unit cell of this AB13 crystal phase. And this phase has been found for big colloids, but also for the nanocrystals and nanoparticle suspensions. And so I always wondered how such a crystal will just form. How does these small spheres know that it has to form these icosahedral clusters, and how do these big spheres know? And if you just look at the hard sphere fluid, you will always see that the big spheres are almost at contact with each other. How do they know that they have to move apart from each other in such a way that these clusters of small spheres fits in between? And so I already discussed that one way to locate the neighborhood of a particle is by just using a simple cutoff distance, and that is all often based on just the first peak or the first minimum in the pair correlation function. But if you now calculate the pair correlation function for the fluid phase and for the AB13 crystal phase, you will immediately notice that the small correlations in both the fluid and the AB13 crystals are not very different, because the icosahedral cluster is also already present in the fluid phase of the small phase. And if you look at the large distance in the fluid and in the crystal, we will immediately see that they are at contact in the fluid phase, whereas they are moved apart in the AB13 crystal phase. So there's not a simple cutoff that one can use to determine the neighbors. And you can still try to calculate all these bond order parameters, and what you immediately see if you plot it in the Q4 or Q6 plane is that all these clouds are overlapping with each other. So it is extremely difficult on the basis of a few bond order parameters to distinguish the AB13 crystal phase from the fluid phase. You can try to do better and then discriminate the different species. In that case, you can distinguish the AB13 large sphere particles from the fluid phase, but still not the small spheres. So and then the question that we ask ourselves is, can we use this using a neural network? And so a neural network is, so in the principal component analysis, that is basically a linear transformation of all these bond order parameters. It tells you what combination of these bond order parameters are very effective to distinguish the different phases. In a neural network, it is basically a non-linear transformation. And so that's what we used. We fed in all the bond order parameters. We also use a cubic rotational invariant of all these spherical harmonics, the so-called WLs. And we also discriminate the different species in all these QLs. And in total, we had 36 values that we fed in for every particle. We first trained this neural network using label data. So we just fed in just AB13 particles from AB13 crystal, small particles from AB13 crystal, fluid particles, and FCC particles. And so it's by training it, you just adjust all the weights and the biases in this neural network. We had to use 2 hidden layers with 72 nodes, and the output layer consists out of 4 nodes. That tells us what the probability is that that particle is the large particle of the AB13 crystal, the small particle of the AB13 crystal, a fluid particle, or an FCC particle. And then by using this training, this neural network, this trained neural network, we were able to look at crystallization of this AB13 crystal. So for that, we use a seeding approach. We start with already a seed of this AB13 crystal that we insert in the supersaturated fluid phase, and we just run simulations at different pressures. If the pressure is then too high, it immediately grows this nucleus. If it is too low, all the trajectories will result in melting of this crystal nucleus. And if you are at a critical pressure of this nucleus, then half of the trajectories will result in melting, and half of the trajectories will result in growing this nucleus further. And that's basically the critical pressure for this critical nucleus. And from the critical pressure, you can calculate the supersaturation, the chemical potential, and the density. And so from there, if you then use classical nucleation theory, you can also determine the Gibbs free energy, the nucleation barrier as a function of supersaturation. So this is, from this data, you can also see that if you go to higher and higher supersaturations, the barrier goes down. And so if the barrier is sufficiently low, so less than 10 kBT, you can just run a spontaneous crystallization trajectory, because at that, if the barrier is sufficiently low, just due to a normal thermal fluctuation, you can find nucleation, spontaneous nucleation. And that's what we did. We tried to extrapolate our data and find the supersaturation where we expect to find spontaneous nucleation. And so here we indeed find spontaneous nucleation of the AB13 crystal in just a hard sphere mixture. So we also analyze this data using our neural network. What we find is that it really starts with an icosahedral cluster of small spheres, then big spheres are attached to it, other icosahedral clusters attached to it, and more big spheres will attach to it. And so if we plot the assembly of the big spheres and the icosahedral clusters, we find that they really co-assembly at the same time in order to form this very peculiar AB13 crystal phase. So this brings me to the next topic, coarse graining. That's also what you always like to do in multiscale modeling. If you consider a colloidal suspension, that are colloidal particles moving around in a solvent. So the solvent we already often treat as a continuum, but you can also tune the interactions by just adding, for instance, depletants or by adding ions. And these ions and these depletants are always a pain to simulate because due to the different time and length scales of the colloidal particles with respect to this microscopic species. And there was very nice work done by Bailey and Parinella in the, where they tried to find better force fields for their atomic systems. They used electronic structure calculation, DFT calculations, and they used a neuron network to, if you start from the spatial coordinates of all the part of all the atoms, you can calculate so-called symmetry functions, which are two-body interactions or three-body interactions, and then you can just train your neural network in order to output the energy of that configuration. So for the training, they have to feed in many, many different configurations, and they have to use labeled data. So for every configuration that they feed in, they already know what the energy is that should come out. And so by training many configurations, they can adjust all the weights and biases of this neural network. They use a step in between the spatial coordinates and then outputting the energy, which are these symmetry functions. And these symmetry functions has to obey several symmetries. They should be translational invariant. They should also be rotational invariant. And also if you swap particles or use permutations, it shouldn't change the outcome. And these are the symmetry functions that they used. So these are just Gaussians at certain distances, and there's a cutoff distance as well that they use. And these are just angular symmetry functions where for every triplet of atoms, you calculate the distances of all the particles, but also the angle between the particles. And they use a set of these symmetry functions to basically fit the energy for many different configurations. So we did the same for colloid polymer mixtures. If you have a colloidal suspension, you can add depletants to it, small polymer coils, and due to the unbalanced osmotic pressure, this gives rise to a depletion attraction. So if polymers cannot come in between these colloidal particles, then they only push from the outside onto the surface of these colloidal particles. That brings these colloidal particles even closer to each other. And so these dashed circles are basically the depletion zones where the center of mass of these polymer coils cannot come. And so if these depletion zones overlap, there's more room available for the polymers, which has and so the polymers have a higher entropy in that case. And all of this basically gives a depletion potential, and the range of this depletion potential is set by the size of the polymers, and the depth of this depletion potential is determined by the concentration of the polymer. And so it's a very nice way to tune the attraction between colloidal particles, but also the strength of the attraction between the colloidal particles. There's an extremely simple model that describes this depletion effect. It was introduced by Frey in 1976. He treated the colloidal particles as just hard spheres. The colloid polymer particles are also described by a hard sphere interaction because the center of mass of this polymer coil cannot come close to a certain distance from the surface of the colloids, and the polymers are just treated as ideal particles, so they can interpenetrate each other and they don't feel each other. And so one can write down the total Hamiltonian of such a binary mixture, which consists of a sum of pair interactions. So for the colloids, polymers, and the Hamiltonian for the polymers is just set to 0 because they are not interacting. And so it's convenient to consider the system in the semi-grand canonical ensemble. So we treat the big spheres, the colloidal particles, canonically, and the polymer grand canonical in such a way that if we integrate out the polymer, the chemical potential for the polymers is already fixed in in the effective Hamiltonian in such a way that we can calculate phase diagrams. And so the thermodynamic potential is just a sum of all the polymer numbers, a trace of the coordinates of the colloids, a trace of the coordinates of the polymers, and then every configuration is weighted with the Boltzmann weight corresponding to the total Hamiltonian. And one can trace out all the polymer degrees of freedom, that is this yellow beast here, in such a way that we end up with only a trace of the big colloids with an effective Hamiltonian. And this effective Hamiltonian is then the bare Hamiltonian of the colloids plus this omega. And this omega is just related to this yellow beast here. What is this yellow beast or this grand potential? This grand potential is the grand potential of the sea of polymer in the external field of the fixed configuration of the colloids at fixed coordinates. And one can also see that this grand potential is nothing else than the free volume, the volume that is available for the polymer. And this free volume can be split into 0 body term, a 1 body term, and 2 body term, and 3 and higher body terms, which are the number of colloids that are simultaneously interacting with this sea of polymers. So the 0 body term is very simple. It is just the total volume of the system, because if there are no colloids, there's no exclusion of volume for the polymer. The 1 body term is just these depletion zones, that the volume that one colloid is excluding for the polymer, and we have n of them. And then if the colloidal particles are close to each other, these overlap zones will overlap with each other, and so this yellow-shaped volume is basically the correction that one has to do. And then the 3 body is the overlap of 3 of these depletion zones, and one of these is this red area here. And so these 3 body interactions are very complicated to calculate. One can only do that numerically because these are very irregular objects to calculate. The 2 body interaction can be calculated analytically. So that's why we used these 3 body and higher body interactions. We calculate them numerically, and we then trained a neural network to evaluate for many configurations this free volume, this 3 and higher body interactions. So here we plotted as a function of the colloid packing fraction. So we fed in many different colloid packing fractions, many different configurations. We trained our procedure, and then we did it for different size rates, 0.4, 0.8, and 1. And we find a very good match of our machine learning fit and of the numerical evaluation of these higher body interactions. Moreover, this machine learning potential that we get, we fitted it for the whole range of colloid densities, and we find that they can be assumed to be state independent. And this is very nice because we can just use this machine learning potential fit for many different colloid densities, but also for many different polymer viscosities. And so one can also use it in order to calculate coexistence using direct coexistence simulations. So we first looked at the structure. If we use this machine learning fit to calculate the structure, the pair correlation function of the colloid polymer and polymer, the symbols are all the machine learning simulations, and the lines are just the original model where we use the full binary mixture. Here we compared the colloidal gas liquid binodals, also with earlier data, and here all the blue symbols are just using the machine learning fit. And we find very good agreement in all of these cases. And this is, I think, remarkable because it's just one machine learning fit that we used to simulate this colloidal gas phase, which is extremely dilute in colloidal particles, in coexistence with an extremely dense colloidal liquid phase. And so the densities are very different for the colloidal particles here, but we only use one machine learning potential. And because we did direct coexistence simulation, we were also able to calculate the interfacial tension using using a very simple area surface calculation. So then finally, yeah, most of our work so far has been based on the standard approach in statistical mechanics. You start with a certain particle shape and the particle interaction. You then determine under which thermodynamic conditions you find a certain structure. And then from the structure, you try to derive the properties of that structure. But because nowadays one can make all kinds of particles, nowadays one can tune the interaction, it would also be nice to be able to turn this logic around. So instead of doing all the forward design, you start with a certain shape, interaction, calculate the structure, and then the properties. Would it be possible also to start with the properties that one desires, then derive the structure that gives rise to these properties, and then if you know which structure gives rise to these properties, can we then find the underlying hemitony that gives rise to this structure? Can we determine the shape and the interactions that will give you that structure? And so this brings me to the question, yeah, can we inverse design a target structure? So that's the last step that I discussed here. And such an inverse design method is based basically on three ingredients. First of all, you need a model with 3 design parameters that will be optimized. One then needs a scheme that updates the design parameters, and one also needs an order parameter that tells you that you have found the target phase in comparison with all these competing phases, and which can be used then as a fitness function in your updated scheme. So the model that we've chosen is just a model that can also give rise to quasi-crystalline behavior, because quasi-crystals are known to be nature's impossible phase. It lacks translational symmetry because there's no repeat unit. So in the case of a crystal, if you are sitting on a particle and you know the units, you know exactly where all the other particles are. In the case of quasi-crystal, there's no repeat unit, and so it's not known where all the particles are. But the quasi-crystal exhibits rotational symmetry, which is characterized by the sharp peaks in the diffraction patterns. And these sharp peaks show a rotational symmetry that is forbidden from a crystallographic point of view. So these quasi-crystals are extremely nice because, yeah, we don't know where the particles are. There are many papers in the literature. Where are the atoms for a quasi-crystal? Structures of quasi-crystals. Where are the atoms? Where are the atoms in quasi-crystals? How are the atoms arranged? Etc. etc. And so we were very intrigued. Can we inverse design without knowing where we should actually place all the particles? And a quasi-crystal. And so we started with a simple model for ligand-stabilized nanoparticles. These nanoparticles consist of a hard core with a diameter of sigma, and then there's a square shoulder around it that mimics this shell of ligands around the nanoparticle. And the shell of ligands has a thickness of delta, and one can change this shoulder with which gives you the length of these ligands. And then, so the shoulder width, the temperature, and the pressure are then the design parameters or the density. And because there are 2 competing length scales in this interaction potential, it gives rise to quasi-crystalline order. So the phase diagrams has been calculated in a temperature density plane. There's a very narrow region of this quasi-crystal phase in 12-volt quasi-crystal. There's also a square phase, and there are 2 hexagonal regions at high density and at low density. And then the rest is just the fluid phase. One can also change the shoulder width. This is the phase diagram for a shoulder width of 1.4 sigma. One can also calculate for 1.27 and 1.60. The most apparent thing that changes is the symmetry of this quasi-crystal. So one can obtain 18-fold quasi-crystals with also 10-fold quasi-crystals by just changing the shoulder width of this potential. And so this is the model that we used with certain design parameters that one can tune. To tune the design parameters, we use a covariance matrix adaptation evolutionary strategy. And this is based on just a Gaussian distribution of all the design parameters. So if we want to tune the temperature and the pressure, we use a bivariate Gaussian distribution. And then the mean and the variance will determine the width and the mean of this Gaussian distribution. And then we draw n samples from this multivariate Gaussians, so n different combinations of temperature and pressures. And for all these state points or these combinations of the design parameters, we just perform computer simulations, and then we evaluate the performance of these different state points in terms of a fitness function. And this evolutionary strategy will then adapt this Gaussian distribution in such a way that it moves towards the highest fitness functions. And it can expand if it doesn't find any reasonable fitness function values, or it can shrink when it has found the maximum fitness function. So the order parameter that we use to distinguish the target phase from all the competing phases is just a convolution neural network that classifies the phases from their diffraction patterns. And diffraction patterns are very nice to discriminate the different crystal structures, but also quasi-crystals have very particular diffraction patterns. It shows these very sharp Bragg peaks with a rotational symmetry that is forbidden from a crystallographic point of view. And so that's how we start our training set. We performed Monte Carlo simulations for all the phases and competing phases. We used the fluid phase, the square phase, the hexagonal phase, and the 3 quasi-crystals. We calculated the diffraction patterns of all of those, and we for many different configurations that we saved for all these different crystal structures. There's one problem here, and that is that these diffraction patterns are not rotational invariant. So we also rotate every training samples by many random angles in such a way that our neural network is able to learn to recognize these phases independent of their orientation. And so we use a convolution neural network, and convolution neural network is very good in distinguishing images. Images are just pixelated particle things, diagrams, and so one can use these diffraction patterns which are pixelated as an input for these convolutional layers. And these convolutional layers tries to extract certain features from these input images. And then if it extracted many different features from that, you can use these features as an input for a fully connected neural network in order to classify this, the different features. And so there are 6 output values that gives you the probability that it belongs to one of these phases. And so this probability that it belongs to one of these phases can then be used as a fitness function for the evolutionary strategy. So here we use the probability that it belongs to this 12-fold quasi-crystal as one of the fitness functions. And so here we started in the fluid phase using this multivariate Gaussian. We pick many different temperatures and pressures drawn from this Gaussian distribution. We performed simulations, we calculated diffraction pattern, and we calculated the fitness function for all these different configurations. And then we update our Gaussian distribution using the evolutionary strategy. And if we continue this for many generations, we will find that the system finds in the end the quasicrystal regime. And so this is the final configuration, and it's indeed a very nice 12-fold quasicrystal. This is the fitness, the mean of this Gaussian distribution, the fitness of that, and we see that within a couple of generations, it already increases very steeply to a fitness function of 1. We can also start in different regions of the phase diagram, for instance, in the square phase or in the hexagonal phase, and in both cases, it doesn't have any problem in finding the 12-fold quasicrystal. We can also change the fitness function to a fitness function that describes the probability that it belongs to the hexagonal phase, so we can also target the crystal phase, and also in that case, it will find the hexagonal crystal phase in the end. We can also change the shoulder width and use that as a design parameter in order to probe the 12, the 10, and the 18-fold quasicrystal. And if we does that, all the final configuration, we indeed find the 12, the 10, and the 18-fold quasicrystal. We then also study the transferability to other models, so without retraining our neural network, can we also use it for a different potential. For that, we use the soft core shoulder potential, which is a continuous potential. And also in this case, if we use as design parameters the temperature and the density, it really finds the quasicrystal regime without any problems. This system has been not very well explored in the literature, so we also use this model to find other quasicrystals, like in the hard sphere, hard shoulder potential. And so we probed, for instance, the 10-fold quasicrystal, and also there we found the discovery of a new phase that was never been reported for this system in the literature. And then finally, we also extended to a 3-dimensional system of smectic phases that also can show quasicrystalline behavior. And for that, we have to feed in 3-dimensional diffraction patterns. By eye, it's very difficult to really probe these 3-dimensional diffraction patterns. You always have to project it on one of the planes, but the neural network doesn't have any problems with 3-dimensional diffraction patterns. And also in this case, it works very well. It finds the 3-dimensional quasicrystal without any problems. And so this already brings me to the conclusion. One can use machine learning to classify phases. We've used and find good order parameters. We've used it to study nucleation in both in experiments and simulations of just plain hard spheres, colloidal hard spheres. But we can also use, for instance, a neural network as an order parameter to study nucleation of a binary crystal. And we can also use it to coarse-grained systems so that we can find very good machine learning potentials that can be used to study phase behavior. And we can also use a convolution neural network to inverse design quasicrystals, liquid crystals, and crystals. And with that, I would like to acknowledge many people. All the simulations were done by Gabriele Colli, Robin van Damme, Emanuele Boattini, and Gerardo Campos Villalobos. Some of them were co-supervised by Laura Villion and René van Rooij. And all the experiments were done by Alfons van Bladeren, Arnoud Imhoff, Patrick Béjou, Enes van der Ween, Anna Nikolankova. And I'd like to acknowledge funding from the ERC grant and from NWO. And I'd like to thank you for your attention.
Right. Thanks very much, Marjolein, for a truly exciting seminar. And now questions, suggestions, comments, whatever are invited from the audience. So who wants to be first? And we have a question from Margarita.
Hello, Marjolein. Sorry, I was late a little bit, not only a few minutes, for good reason. Anyway, it was a very nice seminar. I have a couple of questions. One of them is really stupid, but why do you find mostly these 13 clusters in the fluid phase for the small particles in the first part of the talk? Are there other clusters? Why 13? Is that, I mean, these are hard spheres. So are there some sort of magic clusters? Is 13 just, the most abundant or any other reason?
Yeah, this is already work that Sir Charles Frank from Bristol already proposed. That if you look at the densest local packing of 13 spheres, then this icosahedral cluster gives rise to the densest packing. And this, and because it is abundant in the fluid phase, it also gives rise to glassy behavior, because if you want to go from these icosahedral clusters, which is forbidden from a crystal point of view, you have to make large rearrangements of the particles to find in the end the face of the cubic crystal phase or an hexagonal close-packed crystal. It is not always an icosahedral cluster. They are often defective icosahedral clusters, but there are many five-fold symmetries already present in the fluid phase.
13? Is 13 special in some sense?
Yeah, I think, yeah, if you have 13 spheres, then yeah, if you have one sphere, then only 12 other ones fit around it.
I see. So that's where the 13 comes from. It was just
yeah.
curiosity. My real question is about the last part. It was very nice the way you can identify the quasi-crystals, but I have several questions. I mean, once you have a quasi-crystal, you don't have one, you have infinitely many. So when you choose something with a particular order, which is rotational order, when you train the networks, do you just have one realization? Do you have many? How do you do it? I didn't really quite follow.
Yeah, so when we trained the network, we saved during our simulations about 1,000 configurations. So we already sampled over 1,000 configurations, but they all give rise to this peculiar diffraction pattern with, yeah, if you have a 12-fold quasi-crystal, it has 12 strong Bragg peaks surrounding.
Well, you can get 12. You can have the 12. I mean, the axis of rotation with 12-fold symmetry for many different arrangements of the particles. So my question is, do you actually do that? Do you have many different arrangements of particles with that kind of symmetry? So
yeah. So we use 1,000 different configurations.
Okay, different. That's it. And how large are these? How large are these systems? You never told us in your. It must be huge.
No, we use relatively small systems, about a few hundred particles. So it's not big. No, it really have to recognize these 12 Bragg peaks.
How sharp are they? You can probably do that in simulations. I mean, if they're not very large, how sharp are these peaks? Or you can get R probably or something.
I can show again the knife too.
Oh, never mind. I'll let the others ask the questions. Thank you for the talk and for agreeing to teach us some of your tricks. Thank you. Sometime soon, I hope.
Yeah, I hope so. Yeah, that will be nice.
Okay, bye-bye.
Bye-bye.
Right, thank you. Any more questions from the audience? This is your chance. Questions, praise, criticism, suggestions. Who wants to be next? Who wants to be next? Come on, don't be shy. Well, looks like no one wants to ask any other questions. So Margarita, if you still have questions, you can just keep on asking them.
I'll let Marjolein come visit us and then we can talk. I don't know when travel will be allowed, but in about 6 months, maybe, or less than that. I don't know. I have no idea. But a visit is promised. We'll try
Yeah.
to your calendar. It's difficult to arrange our agendas now because we don't know when it's sufficiently safe.
Yeah. No, it would be very nice to visit you.
No, we
Certain
have,
point. So it's
I was late because I was vaccinated today. So,
yeah.
so- and I could not reschedule it. So I had to anticipate it a little bit, but they only open at 9. And anyway, hopefully I'll survive the vaccine.
Yeah. So which one did you get?
AstraZeneca, because it's I'm no risk for. I mean, I'm less risk
Yeah.
younger people, and I don't have any diseases. So all my friends are the AstraZeneca. Well,
Yeah.
Excuse me, I'm sorry to interrupt, but we are straying a little far from the subject of this seminar. So maybe I can just ask one more time if there are any remaining questions, and then I'll stop the recording if there aren't. Any further questions from the audience, comments, whatever? Well, it looks like there aren't. So let us thank Marjolein again for a very exciting and informative seminar. Thank you, Marjolein. Thank you all for coming, and we'll be back next week. So recording stops now.